Hello everyone and welcome to CRAMSURG, Clinical Research Appraisal and Methodology for Surgical Trainees, where we pick a paper fresh from the press on a hot general surgical topic. We review it for you, we present it for you, we critique its methodology for you, and provide top-of-the-field expert opinions and teaching on research appraisal and methodology. My name is Gio Perrin, and together with Professor Sababala Subramanian, Adam Haig, Ben Wood and Josh Lau, we bring you CRAMSURG from the wonderful region of the Yorkshire and the Humber.
So this is Descriptive Statistics Part 2. If you haven't heard the Part 1 talk, it's there on YouTube, so have a look at it, and hopefully that'll be useful, but I'm going to crack on with this. Right. Just a quick recap of what we learned in Part 1. So we talked about data types, we talked about normal distribution, and the parameters that are used to describe the data based on the data type and the normal distribution. So this is what we talked about last time. And in this talk, we're going to talk about graphs, charts, and tables, and the appropriate graph, chart, or table to use when you describe data or when you're reading a paper to decide on what's appropriate and what may not be. So before we go into graphs, charts, and tables, I thought we should revisit data types because a lot depends on data type. So this is the slightly complex table that we discussed in the last talk. And I'm just going to ask you to focus on the differences between categorical data and measurement or scale data, also called quantitative data. So categorical data is basically data that is nominal or ordinal, which is qualitative. In other words, you're putting the values into categories. So a good example would be gender, male or female. Another example would be city in the UK, Edinburgh, London, Glasgow, and so on. So those are data types wherein you put the values into categories, so you don't measure them. And on the other hand, measurement or scale data or quantitative data is something that you can count. And there are a couple of different types of these, but we won't go into this detail in this talk. So moving on to graphs, charts, and tables. So in a report, a graph, chart, or table should be there for a specific objective. It should be obviously relevant and clear. It should improve the reader's understanding of the data, and it should add to the results section to enhance it, to improve it. Now, you could either use tables or charts and graphs, and for the same kind of data that you want to describe, you could use one of the two, and they're often interchangeable. But in some settings, a table is preferable, and in some other settings, a chart or graph is preferable. For example, charts and graphs are better if you want to depict certain complex relationships, and also sometimes where space is an issue. And often space is an issue if you are asked to do a really short presentation and you're given restrictions on the amount of time and therefore the number of slides you're going to use. And if you're going to publish a paper where often the journal would say you can only have 3,000 words, or you can only have up to 3 or 4 printed pages, and so on. Tables, however, are better for describing a mixture of data types, and I'll show you an example. And also, if you wanted to be very specific about the exact values, or if you want to give precise values, then obviously a table would be preferable. Right. So why use charts, graphs, and tables in the first place? I mean, this is self-explanatory. Obviously, it facilitates communication and improves understanding of the data that you're trying to describe. And you're structuring the data that is to be presented, and you're improving the clarity of the presentation by using charts, graphs, and tables. The other reason for using these charts, graphs, and tables are to reduce reader time in assimilating information. So rather than go through 2 or 3 pages of results, you could look at a couple of graphs and tables and get the information you need. And many of us don't read all of the text in a paper. We go straight to the graphs and tables and try and get the information we need, and we move on. And they also help reduce word count and space in a report, in a paper. And a good graph or chart can encourage a reader to investigate the paper further, just like a good abstract. So if you glance or if you happen to read an abstract and you find it interesting, then you might, in some instances, be interested in spending the time to get the full text and look at the paper in more detail. Similarly, you often find graphs and charts on online searches. Sometimes journals allow you free access to graphs and charts, but don't give you full access to the paper. And the graph and chart or chart is really good, and you might want to go to the library or try and get the paper to look at it. So that's another purpose. So in general, what constitutes a good quality chart or graph? The important thing here is that this should be standalone and it should be meaningful on its own, which means that if you're looking at a table or a chart, you don't want to be going back and forth to the text to try and figure out what that chart or table is about. The chart, with its heading and with the labeling and footnotes if necessary, should provide all of the information you need. So all parts should be clearly explained, and when I mean parts, and again I'll show you some examples, I mean the heading or the legend or the caption, the footnote if one is necessary, if it is a table, then the headings of the columns and rows, and so on and so forth. Professional, even if it's your first paper that you're publishing, it should appear professional. Why? Because the appearance of a professional graph or chart implies good quality. It doesn't always mean good quality, but it does give the impression of good quality. And it also implies that the author has taken time and has taken care in preparing the chart. And a good chart or graph should keep the reader at the focus of the data that's presented. Just like a patient should be the focus of your clinical encounter. And what I mean by this is that you do not want to display data or present data just because you have it. You might have done a PhD and you might have tons of data that you want to show to somebody, but that is not a good reason to put the data in a paper if it's not specifically relevant to the research question. Right, before you start, think about, is a graph or a chart necessary? Think about, does it actually add to the results section? Does it complement it without duplication of the text? And think about, am I clear in what I wish to present? Do I know, can I foresee what the graph or chart should show? Okay. Now, let's start off with tables, talking about tables for a minute or two. So here's a table. And this is a table showing some baseline features in Graves' disease. The table heading says, right? And it's got some characteristics that is being compared in two different groups of patients. And there is some data such as male and female ratio and RAA use, whatever that is, and consultants. This is data that is qualitative, and then there is age, duration of surgery, and hospital stay after surgery, which is quantitative. So there's a mixture of data types. Okay, so let's see what the problems are in this table. Firstly, the heading doesn't really give you a full picture as to what the table is about. So heading should give a clear overview without you having to go back and forth to the text. So I would expect something like clinical and surgical characteristics of patients with Graves' disease who are undergoing surgery or who have had anti-thyroid treatment or whatever it is, right? Avoid using abbreviations like MF, male and female, RIA, which probably refers to radioiodine ablation here. But if you're going to use abbreviations, put them down in a footnote. Use footnotes and expand your abbreviations and add any caveats or notes. And there are several that's missing in this table. Beware of your numbers. So obviously there's a mistake here, so make sure that the numbers are accurate. Headings, the column headings and row headings should be clear, and it should be mutually exclusive. Okay. And if you're going to enhance certain text, you need to add a footnote to explain what it is. And if you're going to put some asterisks here, then you need to explain what they refer to. Okay, so there are quite a few problems in this table. And there's another one here, and there are some figures within brackets, and they probably refer to range or interquartile range, but it's not being explained. Okay, right. More, so you've got some cells here, and this particular row is quite wide compared to other rows, so the cells really should be equally spaced. And you can see an alignment problem here. In this particular column that I'm highlighting, they're all aligned in the center, whereas in these other columns they're aligned to the left. And you'll find that you will encounter a lot of these problems very commonly in surgical literature. And just taking a little bit of time in preparing these tables properly goes a long way in creating a good impression. Right, so things to remember: ensure that a clear and comprehensive heading and footnote is present. Ensure that the content is complete and accurate. We make sure that the row and column headings are clear and consistent with the content of the cells. And we make sure that all acronyms are explained. It's also useful to use shading and bordering and highlighting to enhance the headings of the columns and rows, and also sometimes highlighting areas that you want the reader to focus upon. But if you're highlighting something, then add a footnote to say what is it you've highlighted and why. And that helps rapid processing of the information that the reader is coming across. Okay, things to avoid. Avoid too much data and too small font sizes. If you have a lot of data and you're trying to put them all in one table and reducing the font, that usually means that you probably need more tables. Avoid too little data. If you have too little data, maybe just one row or two rows in a table, you have to think about whether you really need a table or whether you can simply present that in your results section as text. It's really important to avoid data that is not essential and to avoid duplication with figures and text. And in tables, although tables are often used to give precise values, you want to avoid too much precision. Like, for example, you don't want to put down that the p-value is 0.0123. At the same time, you don't want to describe median length of stay, for example, as 3.4 days. Just 3 days would be sufficient. So much for tables. Let's move on to charts and graphs. As you've probably all heard, a picture is worth 1,000 words. So charts and graphs are really important. And I just thought we'll dwell a little bit on charts, graphs, and plots. Are they all one and the same? They are used interchangeably. So for all practical reasons, you can consider that they are the same. However, there are subtle differences. Charts are used to describe just one variable, whereas graphs describe more than one variable or relationships between variables. And plots are ideally used when you are talking about points being plotted on a graph using coordinates like x and y axis and so on. But you'll be forgiven for using these words interchangeably, so I wouldn't worry too much. Now, there are a number of different types of charts and graphs and plots. Each software that you use to generate these, from Excel to SPSS to GraphPad, Prism, and so on, you will find so many options, and often it's a bit confusing as to what to go for when you've got your results, you've got your spreadsheet, and you're writing your first paper, and you think, where do I start? It's useful to think about what's the main purpose of using a chart or a graph or a table. And I tend to think of this main purpose as one of three different sort of questions. Do I want to describe the distribution of a variable? Do I want to explain the average, the spread, or the frequencies? Do I want to describe the relationship between two variables? Is that why I want a graph? Or do I simply want to describe changes in one variable or multiple variables over time? So if you just think about this, then you can move on to deciding on the appropriate type of chart or graph to use. Okay, right. So those are the three questions: describing distribution, describing relationships, and describing changes over time. If you're describing distribution, have a think about what kind of data type it is. Is it categorical data? If it's categorical data and you've only got one variable, then you can use pie charts or bar or column charts. If you've got two variables and you can't use a pie chart, I'll come to this again in a minute. So the typical thing to use is a bar or column chart. You might have heard of charts called pictographs and dot plots. These are rarely used these days, so we'll leave them be. If you have quantitative data and you want to describe it, if the data is normally distributed, remember we discussed normal distribution before, then you could use a histogram. If the data is not normally distributed, then you would use a box and whisker plot. So much for describing distribution of the variable that you're interested in. Now, if you've got two or more variables and you want to describe relationships, then again, think about whether the data is categorical or quantitative or measurement. If it's categorical, you could use cluster bar chart or stacked bar chart. I'll show you an example. If it's so I'll go back one step. So when I said it is categorical, I meant both variables. So if both variables are categorical, then you use a cluster or a stack. One of the variables is categorical and the other is quantitative, and you want to describe the relationship between the two, then you could use either what we call an overlapping histogram or box and whisker plots, depending on whether it's normally distributed or whether it's not normally distributed. Okay. If both of the variables are quantitative, then most people would use a scatter plot, and I'll show you an example. If you then want to describe changes over time, in other words, if you're looking at an event that happens over time, like we often do, like we've got recurrence of a particular problem or death, and so on, then that we refer to as time to event data, and we typically use survival curves. We discussed survival curves in one of our previous talks. I'll come and describe that again very briefly in a few minutes. And if you have a quantitative variable that you want to describe how it has changed over time, then you use something called a line graph. Okay, so these are the graphs that are commonly used in clinical or medical literature. There are a number of other types of charts and graphs, but we won't talk about them because they're very, very rarely used. Okay, now I hope you're still with me. So let's look at some examples. So, assuming that you wanted to talk about distribution of a data and the data is categorical, a commonly used chart is the pie chart. There are different types of pie charts. The one on the left is a standard pie chart. The next one is what we call a donut chart, where there's a gap in the middle and you can use the gap for putting some text in. There's a pie chart that is 3D, and then there's a pie chart that's called an exploding pie chart. Now, most people would advise you to keep things simple. So avoid 3D pie charts or exploding pie charts and so on and so forth. Just try and keep things as simple as possible. That's usually best when it comes to depicting data. And also avoid pie charts for categorical data with more than half a dozen categories. It just looks very cluttered, and the message that you want to give is often lost. If you have 20 or 30 different categories, different levels for a particular category, then a pie chart is really not that useful. Okay. So we're going to move on to another kind of chart for describing the distribution of categorical data, called the bar chart, also called the column chart, right? So if you've got just one variable, say time of diagnosis, and you've got intraoperative, postoperative, preoperative, they're not in the right order, and you just want to describe the numbers of patients in each of this category, then you can use a simple bar chart that I'm highlighting in the top left of the screen. Okay. Now, if you want to describe the distribution of two variables, and you're just describing the distribution of these two variables, the variables being time of diagnosis, that I'm highlighting on the x-axis, in across genders, i.e. male and female, then you can use what we call a clustered bar chart or a stacked bar chart, which is the bottom. Okay, so again, bar charts are very commonly used for describing categorical data in one or two or sometimes three different variables. Okay. Now, what if the data is quantitative and you want to describe it, quantitative data? Now, like I said before, if the quantitative data is normally distributed, you would use what we call a histogram, or you could use a histogram. And if the data is not normally distributed, the thing to use would be what we call a box and whisker plot. So let's go through this in a little bit more detail. So here's a histogram of age at diagnosis of a rare cancer. This is data from a systematic review, right? Now, you could plot a histogram and check whether the data is normally distributed or not. And again, I won't delve into this because we've covered this before. So a histogram is often used to check for normality, right? But you don't often see histograms in reports. Why? Because you could easily describe this data or the age at diagnosis using text. You could simply say what the mean is and what the standard deviation is and be done with it. You could do that in one line and you've saved yourself a lot of space. And it's usually not necessary to represent the data in a graphical form. If all you want to describe is the distribution of the data, you can simply say what the mean is and what the standard deviation is. Okay, so that's why you don't often see histograms in papers in medical literature. Right, now here you do see box plots more often. Box plots are used to describe the distribution of data that is quantitative but not normally distributed, right? So let's look at the different parts of a box plot. So this is important. We use it not too uncommonly. So the box, the lower edge of the box represents the 25th centile, right? The upper edge of the box represents the 75th percentile. There's a line through the box that represents the median. So this is not the mean, this is the median, because you're talking of data that is not normally distributed. The median is not always right in the middle of the box. It's often skewed. In this particular figure, it appears to be in the middle, but it's not often the case. The whiskers, if you like, represent the minimum and the maximum data point. Now, the lower end of the whisker usually represents a minimum data point that is not an outlier, and the upper end represents the maximum data point that is not an outlier. Now, what do I mean by outlier? Sometimes you find certain values way away from the rest of the data, and traditionally values that are outside 1.5 times the interquartile range are described as outliers. That is traditionally. Now, in this data set, there are no outliers, and in some instances, some people do not depict outliers. They simply extend the whisker up to the lowermost value for the minimum and the uppermost value for the maximum. So it is useful to remember the meanings of these various lines. So the box, the upper and lower edges of the box refer to the 25th and the 75th percentile, and the whiskers go up to the minimum and maximum data points that are not outliers. Okay, so I hope that makes some sense. Right, we'll carry on with our discussion of charts. Now, we've talked about describing the distribution of data so far. Now we then move on to the second objective of charts and graphs, which is describing relationships. So if it's categorical data, to describe the relationships between two sets of categorical data, we use bar charts. I've already highlighted this before. So you've got the stacked bar chart on the left and the clustered bar chart on the right. And essentially here they're describing the relationship between gender, which is categorical, and time of diagnosis, which is also categorical. Okay. So if you want to describe the relationship between a categorical data type and a quantitative data type, then you've either got the histogram for normally distributed data on the left, or you've got the box and whisker plot for data that is not normally distributed. Okay, and when we say normally distributed or not normally distributed, we are referring to quantitative data. And here in this example, the quantitative data is age at diagnosis. Okay, and you're comparing age at diagnosis across gender, i.e. in men and women, right? If you're happy that your age at diagnosis is normally distributed, you can use a histogram. Well, there are two histograms here. This is called an overlapping histogram, one for females and one for males. If you're not happy with the distribution being normal, then you assume it's not normally distributed and you draw a box and whisker plot for males and a box and whisker plot for females separate. Compare them. And you're looking at the relationship between across genders. Right. If you want to describe the relationships between two sets of two variables that are both quantitative, then you plot what we call a scatter plot. You've probably seen scatter plots on a number of occasions. Here we've got a scatter plot comparing age at diagnosis, which is quantitative, and quality of life, which is also quantitative. This is a typical example where you would plot a scatter plot. Remember that in a scatter plot, you shouldn't draw a line, a regression line, because here you're simply describing the relationship between two sets of data. You're not trying to infer or predict one data from another. Okay. Right. Now, changes over time. So if you want to describe a variable that changes over time, and that variable is a categorical or binomial variable such as death or recurrence, then you plot what we call a survival curve. We've discussed survival curves before. I think in the talk on measures of risk, we talked about survival curves and hazard ratios and so on. So I won't dwell on this. But remember that if you want to look at a binary variable or a categorical variable with two categories, and you want to look at that event that happens over time, then you think of a survival curve. So that's the kind of graph that you would want to use. Essentially, on the x-axis, you have the time, and here it's time to death or metastasis. And on the y-axis, you have the cumulative survival, which reflects the fact that you start off your study with all patients being alive, and then over time, as patients develop an event, which is death or metastasis here, then the cumulative survival starts to go down. Okay. Now, if you wish to describe changes over time of a quantitative variable, then you can use a simple graph called the line graph. And this line graph here shows a number of cases of a rare condition seen in a big region, if you like, over a span of several years. So for each year, you've got a number of cases, and you just join all of those dots and you get a line graph. So this depicts change in a quantitative data over time. Right. So what are the tips and tricks for a good chart or graph? Now, just like with tables, it's important to have a very clear and a complete heading or legend or caption. Avoid graphs with too little or too much data, and you think whether you really need a graph in the first place. Avoid unexplained abbreviations. Some people say avoid red and green pairings because people who are colorblind would struggle. So that's just something to keep in mind. And I would emphasize that you reduce unnecessary design elements. So there's a lot of you have at your disposal all these software that allow you to produce really complex looking graphs. And unless you really have a need for the complexity, go for the simple ones. Graphs should almost always show raw data, not summary data. There are some people that display summary data such as median and mean using bar charts. They are to be discouraged. You really want to restrict the use of bar charts to categorical data. You don't want to depict median or mean that way. There are other ways of doing it. For example, if you want to depict medians across different groups, you would use the box and whisker plot. Okay. Now, sometimes when you have a graph and there are lots of elements to it, and you want to put some labels in, you want to have grid lines, and you want to have markers or asterisks and so on, that's all fine. They should complement a good chart or graph, but they shouldn't really hide or mask the important lines, bars, and data points. So keep that in mind. Right, we've come to the summary now. So we've seen that there are several ways of describing data using tables and graphs. The important thing to keep in mind is that for a given data set, you could use a number of different types of graphs or charts. Some, however, might not be appropriate, and the appropriateness really depends on the type of data, the purpose of using the graph or the chart. What's the purpose of describing the data, and in some instances an understanding of the distribution, whether the data is normally distributed or not, if it's a quantitative variable. Okay, so next time we'll talk about an example, and we'll revisit the appropriate use of tables and charts with an example. And I'll talk about a special type of table called contingency table, and a couple of special graphs called forest plots and funnel plots you've probably heard of. I think that'll complete our lecture on descriptive statistics.
Thank you everyone for tuning in and listening. Until next time, keep running your life with our surgical podcast.